So today we're looking more at the data analysis side of gravitational wave astronomy. And it's a pleasure to introduce Dr. Alessandra Papa. Alessandra studied physics in Rome, received her doctorate from the University of Rome, Tor Vergata in 1997. As a postdoc, Alessandra worked at INFN laboratories in Frascati, Italy, and in AEI in Potsdam, where she has been a postdoctoral fellow and staff scientist since 2005. From 2000 to 2005, she held visiting professor positions at the University of Wisconsin, Milwaukee, and was appointed tenured senior staff scientist there. Since 2007, Alessandra has led a research group on gravitational wave data analysis at the AEI. She still holds a part-time adjunct professorship at UWM. In 2014, Alessandra was elected Fellow of the American Physical Society. From mid-2006 to late 2013, Alessandra served as the LIGO Scientific Collaboration Chair of the LSC Virgo Data Analysis Council. This working group is responsible for proposing scientific priorities to the LSC and Virgo collaborations and for coordinating the overall gravitational wave data analysis efforts. Since 2014, she has chaired the Coherent Waveburst Review Team in the LSC. The Coherent Waveburst search identified the first gravitational wave signal within 3 minutes of data acquisition. Alessandra was also a member of the team of 6 LSC members, which was appointed to coordinate the writing of the first gravitational wave detection paper. Alessandra is one of the principal investigators of the Einstein at Home volunteering computer project. Alessandra.
Good morning. Right, so I am going to talk to you about continuous gravitational waves, and in particular about our efforts to try and detect them. And I know that Alicia Sintes, who was here last week, has already given sort of a first introduction to the topic. It's hard when one is asked to give lectures of this kind to try and tune them to the audience properly, because I know here you come from quite different backgrounds. So I figured the ones of you who are closer to data analysis are probably going to know a lot of the things I'm going to talk about. But for the rest, what I'm trying to do is I thought about the types of things that my students, when they begin working with me, are confused about. And so the important concept that they have to absorb in order to be able to work and just be able even to read LIGO's observational papers. And even though I'm going to illustrate them in the context of searches for continuous waves, a lot of these concepts, of course, apply to all the other searches. Okay? Well, you've heard about me already, and I thought I would start telling you something about myself, but let's see. I think the thing that you didn't hear about was my, so this is my research group, a photo taken this winter in Germany, northern Germany, so we see we're all bundled up. This is the webpage of the Albert Einstein Institute. This is the largest institute devoted to general relativity in the world, and it spans many different topics, from research in mathematical general relativity to applied interferometry development for new detectors and data analysis. And data analysis, we look for different types of signals, and my group here is the one that looks for continuous gravitational wave signals. I don't just do research in physics. I actually also have a family, a normal life, and interests which are not just the physics. But now this is what we need to talk about. So, what signals may be detectable by LIGO? Well, let me just, yeah. Ooh, what did I do? Here's the pointer, yes. So I'm sure you've seen this plenty of times. This is the LIGO noise curve, and it is in fact the noise curve, and I'm pointing to the red and the blue curves from Hanford and Livingston during '01, which was the first run of the advanced detectors. On the x-axis you have the frequency, on the y-axis you have the noise content, and what I wanted to just point out here is that the high sensitivity region of these detectors goes from a few tens of hertz to about a kilohertz, 1500 hertz, okay? So this tells you something about the typical time scales for the processes that would be emitting signals that we are most likely to detect. That's because that's where our instrument is the most sensitive. And so these must be time scales of seconds to milliseconds. And in this sort of broad category of possible signals, historically, they have been sort of split in 4 groups because the techniques that we used to look for them were somewhat different. So signal from compact binary in spirals, unmodeled bursts, the short bursts of gravitational radiation, for which it's hard to actually have a model waveform, continuous quasi-periodic gravitational waves, and stochastic backgrounds. This is how we looked at things 20 years ago. Of course, as we matured our analysis methods and we did a lot of analysis, the boundaries between these have become a lot less sharp. And I would say there is a continuum now of type of signal shapes that we look for. But this is the origin. It's really historical because there was sort of 4 basic different approaches. So I'm sure you've heard this already from Alicia, but I'm just going to recap it for you. Continuous waves are, you can think of them as nearly perfectly monochromatic trains of gravitational waves. Actually, nearly perfectly monochromatic because there is typically a small spin down. And these, you can think of them as emitted by a neutron star, a compact object, as it rotates, when it presents a deformation from a spherical shape. And this typically we describe by quadrupolar ellipticity, epsilon. Now, ellipticity values are highly uncertain and may reach values as high as 10 to the minus 4, although I would say that this is rather optimistic and speculative. And the fact that somebody's envisaged that neutron star models can be built that are stable with this ellipticity doesn't mean actually that they exist. But now I put this number up, not so much because I want to discuss ellipticity numbers, but to put a number in your head for when we'll look at observational results. Okay? So remember, roughly 10 to the minus 4, possible, but extremely, extremely high. Actually, I would guess that most neutron star experts would say very unlikely. And with this type of emission model, which this little bump, the quadrupolar ellipticity and the star rotating, and this is the thing that's responsible for the emission, the gravitational wave frequency is twice the rotation frequency. Okay? And the gravitational wave amplitude here, as you can see, is proportional to the ellipticity. This is the principal moment of inertia of the object, and this is the square of the gravitational wave signal, okay? So it's the thing that's twice the rotation frequency, and obviously inversely proportional to the distance. So the closer the object, the better, obviously. Now, conceptually, what does it mean to search for a continuous wave signal? Well, like in most of the templated searches that we do, so the searches for which we have a signal wave shape model, you can think of the process as a black box that has some knobs. And the knobs are the parameters that describe the wave shape. And in the case of a continuous wave, it's the frequency and frequency derivatives, first derivative, second derivative. Typically in our searches, we do not go further than the second time derivative. That's enough. The position in the sky, the inclination angle, the polarization angle, and initial phase, and the amplitude. Okay? So these parameters here are typically all you need to describe a continuous gravitational wave. And so you set up a machinery that, depending on the value of the particular waveform that you want to look for, takes the data and spits out a result. And we'll see what that result is. Now, you see here I put an asterisk to the machinery, because if you notice, there's fewer parameters here than there are up here. Okay? So the reason is that actually we do not explicitly need to search over these 4 parameters. They're called amplitude parameters, or sometimes nuisance parameters, because one can set up this machinery in a clever way that analytically maximizes over these. Okay? So it's clever because this means you don't need to explicitly search over them, so you can save computations. It looks at the data and automatically gives you a value of this result, sort of the score. How likely is it that this data contains a signal with these parameters? That's maximized over these here. And I think Alicia derived the F statistic, right, for you. And she showed you how this maximization in that case is done. So anyway, when you think about a search for continuous gravitational waves, actually this also applies to a search for binary spirals. Think of a machine where you input the parameters that describe the waveform, give it the data, spits out a result. Now, let's look at the result of the search. So this is a detection statistic. What is it? It's basically a score that tells you how likely it is that in the data there is a signal with the parameters that you're actually looking for. When the data contains noise, as it's in our case, since it's mostly noise in fact, this score is a random variable. And so the detection statistic is just the realization of a particular random variable. If the noise is Gaussian, it doesn't contain disturbances, based on how the detection statistic is constructed, the value that we will get for the score, okay, will be a realization of the theoretical probability density function associated with that detection statistic, which you can derive analytically. And so based on the value of the random variable, that measurement that you have, we can decide whether the data contains a signal or not. So I am going to remind you some basics about some important quantities in signal detection. And it is, how do we decide that we have detected something? Well, let's see. Let me take as a detection statistic the F statistic, okay? 2F, if the noise were perfectly Gaussian, would be a chi-squared with 4 degrees of freedom. And in this case here, you can see it is there. What I've drawn here is the value of 2F on the x-axis. On the y-axis is the PDF, the probability density function. And this is the probability density function for a chi-squared with 4 degrees of freedom. Okay? So you can see that, as you would expect, the expected value is 4. The model value is 4. Okay? So suppose that we were testing one point in parameter space. So had we one specific waveform we were looking for, we'd done our search, and out comes a measured value, which is 4.3 from the data. And we have to decide, is this a detection or not? Well, this is standard hypothesis testing. You see where 4.3 lies in this PDF, okay? And you see that there is 16% chance that noise alone would have produced a value of the detection statistic, which is at least as significant as the one you've measured. So you conclude that this is not a defensible detection candidate because noise alone would have produced something as significant as that, or even more, in 16% of the, of 60% of chance trials. all right? So this is, concept of false alarm probability associated with one specific measured value of the detection statistic. What would something that looks like a confident detection look like? Okay, so here's again our noise PDF. And imagine that instead of 4.3, we measure 7.9. All right? If we look, what is the chance probability of measuring 7.9 if the distribution is due to noise? If you do that, you basically get 0. And to give you an idea of a number, if the chance probability of measuring something equal or greater to 6 is 2 times 10 to the minus 9. So by the time it gets to 7.9 is 0. So that, in fact, would be something that stands out of the noise. It means that if this were the actual distribution of the noise, which is something you'd have to test, because usually the data is not so well behaved, so it's not as easy as this. But if you could be confident this is the distribution of the noise, this would be an extremely significant finding, okay? If you had done only one search. If you knew somehow that this was an interesting waveform to look for, somebody had told you, perhaps it's the waveform that you expect associated to a non-pulsar, and you measured this value, you can start getting excited, okay? And in fact here, I just plotted for illustration, this is the PDF that one would expect from noise plus a signal with SNR about 3.4. And you can see that the bulk of the probability density to the left of the measured value is quite high, 84.6. So this could give you a sense of what SNR could be associated to this event if this were a signal, okay? So just to get you thinking about the type of reasoning that is associated to the results from an analysis. Now, I want to spend some time talking about something important, which is the trials factor, which is very important in continuous gravitational waves because of the reasons that I will explain in the next hour or so. So, let's proceed. As I said, a waveform is typically defined by all these parameters. And in many instances, it's interesting not to look for continuous waves from objects that we know about. That means for objects for which we know the position, we know the frequency evolution, okay? But actually to ask ourselves, is there something out there that we do not know of? And I'll go back to this. And so what we do is that we have to set up template banks. It means we have to do the search for many, many different waveforms. And so we get many values of the detection statistic, one for each of the waveforms that we searched. Now, if we're lucky, we expect to find one signal, okay? So this means that our data set is noise dominated, okay? We look at the results, and if at most, we hope to find one. But most of our detection statistic results are going to be representations of the noise. So you get something like this. Here what I've shown is, let's say, two arbitrary axes. Okay, could be two of the search parameters. And here are the detection statistic values. And the question is there a signal here? Now, this is actually fairly well-behaved noise. Well-behaved in the sense that it has uniform statistical properties. So it'll be a question to ask whether these statistical properties are the ones that you would expect according to the detection statistic that you built, if they actually follow the theoretical one. But at least when you look at them by eye, you don't see disturbances popping up in different regions of the parameter space. So to zero order, this looks like possibly a fairly well-behaved data set. And you know it's mostly dominated by noise, but there might be a signal in there, perhaps just sticking a little bit above the noise. So you're your bet is that your signal is going to be one of these higher ones, right? Because it's the one that matches best, you know, the possible waveform. So you're going to pick the maximum, and then you're going to, and when you ask yourself, so how significant is it? You have to confront this, this fact. Suppose that you search for 200 templates, okay? You see the maximum is going to be around 2.5. Good. Now suppose you search 2,000 templates. The maximum now is going to be around 3.5. Suppose that you search for 80,000 templates. The maximum is going to be nearly 5. And the maximum here is just a maximum due to random noise fluctuations. Okay? So just noise fluctuations alone, depending on how many trials you've performed, or how many templates you've searched for, increases. So although this is completely obvious, this has a profound consequence, which is if you want your detection to have a fixed significance, you want, let's say, a 6 sigma significance. If you do 200 trials, your signal is going to have to fight with noise fluctuations that at most are going to be 2.5. So a 5 sigma event perhaps is at 5. But if you're doing 2,000 trials and you want the same 5 sigma significance, your signal is going to have to be 7. If you're doing 80,000 trials and you want a detection at the 5 sigma significance, your poor signal has to fight against fluctuations that can be as high as 5, and so will have to be 10. Okay? So what this means is that as the number of search template increases, if we want the same significance, the minimum detectable signal has to increase. It means that we lose sensitivity. Okay? So there is no such thing as a universal sensitivity of a certain category of searches. It depends on how many trials you do. If you only search for one waveform, because for some reason you have reasons to believe that that is a special one that you expect, that is great, because it means that in order to be able to make a confident detection, you need a smaller signal than if you looked over 10 to the 16 different waveforms. Okay?
Excuse me. So what do you do in a case where, just from the CBC side, say you did a search for just the binary neutron stars, and I don't know, looking at maybe 10,000 templates, and you found something that was a 5 sigma significance, but then you compared that to one of the full parameter, or I guess the O2 template bank searches, which is like 650,000 templates, and you saw that it only had like a 1 or 2 sigma significance. Would that be cause to worry, or would you expect that large of a fluctuation?
Well, and this is why I talked about trials factors, and this is where this comes in. And so it is taken into account. And so the significance of an event that is found in a search where you've done a factor of, 10, 100, 1,000, 10,000 more trials and templates with respect to a search with less is taken into account, and the significance is decreased.
I guess what I mean, though, is wouldn't that be cause to worry that something's gone wrong to have that big of a difference between two searches? Like if a BNS search found some high significant candidate, but something that was looking for BNS, BBH, and INBH said that's a really small fluctuation.
Well, I mean, all this when CBC searches do their significance estimates, they do factor in the number of trials that have been performed. And so it could be, I don't know if with the specific numbers you mentioned it would be, I would have to look carefully, but this is a check that is done. And so the question is asked. This is what I'm saying.
So does this essentially mean that since we are probing the parameter space more accurately, we need better certain signal to noise? Like, I'm still like trying to wrap my head around what you just told us. It's a bit like, it seems like counterintuitive in a way. I don't know, maybe it's just because I have
it's not
no
really,
experience with it.
well, if you want, it is more accurately. For example, you can have more templates for different reasons. One is that at a fixed, let's say, search setup, so resolutions in the template banks, you just want to search a broader parameter space. For example, for continuous wave signal, you could say, I don't want to search just 100 hertz, I want to search 1,000 hertz. The template bank increases in size, so the number of trials that you're going to do are going to increase. This doesn't mean that you probe the parameter space more accurately, it just means that the parameter space is broader. Or you could say, I want to stick to the 100 hertz that are interesting to me for some reason, and I am going to design a search setup where I am actually going to grid the parameter space more finely, because, for example, I'm using longer coherent observation times that require a finer resolution. So that's a way in which, in fact, you are probing the parameter space with a finer resolution, which is the question that you're asking. From the perspective of the trials factor, meaning the fact that for either because I'm increasing the resolution or because I'm broadening the parameter space, I am actually searching more templates, the effect is exactly the same. I am doing more independent trials. So if I measure something which is significant, and I want the significance to be the same, let's say a 5 sigma significance, the signal will have to be higher the broader, the more templates, the more independent templates I've searched. And this doesn't matter whether it's more independent templates because I've used a finer resolution, because, for example, I increased the observation time, or if it's a larger number of independent templates simply because I've decided to investigate a broader parameter space. This is something that we can talk about more, think about it. This is something which I think my students are often confused about it. And so I thought I would actually spend a few slides explaining it. And in continuous waves, it has far-reaching consequences, especially because the parameter space is so huge, at least for certain types of searches. So another thing I wanted to talk about are upper limits. And this is because you will read about upper limits in all of the LIGO papers. Upper limits can be set in different ways, and typically is what, we've had 20 years of experience in setting upper limits, because only last year we saw something. And some of us haven't really had that moment of thrill yet to seeing the signal that they've been looking for, so we continue to set upper limits. And I think it's important that the concept is clear. So this is what I'm going to tell you about. So suppose you don't see anything. Can a null result tell us anything? And yes, of course. And they can tell us something about what is not there. Whether that is interesting or not, again, it depends on the sensitivity of the search, and so on the consequences on the astrophysical parameters of what we have not seen. Is it interesting to say that we haven't seen a pulsar with an ellipticity of 10 to the minus 2? Well, the answer is, would it be interesting to say, we haven't seen a pulsar with an ellipticity which is larger than 10 to the minus 2? The answer is no, that would not be interesting, because I showed you at the beginning that a very optimistic value for the ellipticity is 10 to the minus 4. So if our upper limit constrained the ellipticities to be larger than 10 to the minus 2, well, sorry, that would not be such an interesting result. But in fact, this is not where we are. Our upper limits now are starting to constrain, for example, the ellipticities of the objects to values that are something that perhaps Neo wouldn't completely roll on the floor and laugh and said, well, I didn't need you to do the analysis to tell me that, you know, we don't have objects that bumpy. So how do we set upper limits? Let's go back to our results plot. And let me say this is the position in the sky. These are the detection statistic values. And these are all the detection statistic values for all frequency and frequency derivatives as a function of the position. And as you can see, there's nothing that sticks out particularly in here, right? Nothing that you could say, yes, this is our 5 sigma detection because it stands out of the noise so much. This is something that's so much more consistent with the signal than with the noise. This is all the fluctuations are similar. And the highest one is this. It's this, I put a star, 2F star value. And so how do we set the upper limit? Well, we pretend that this were due to a signal, okay? And then we ask the question, what is the smallest amplitude that would produce such value here? So what is the smallest signal amplitude such that if we had a signal with that amplitude, would measure a 2F star value this large? Now, it might seem a trivial question. It actually, there's a little bit of work that one needs to do because the value of the detection statistic that we measure doesn't just depend on the amplitude, H0, of the signal. It depends on the frequency through the sensitivity of the detector, the position in the sky, the inclination angle, and the polarization that then governs the way that the particular wave couples to the detector. So when we measure a certain value and we want to determine the smallest H0 that would produce it, we have to factor in all these elements. So what do? We imagine a population of sources. Imagine for a moment that this set of results came from a really small frequency band, let's say 0.5 hertz, such that the detector sensitivity is basically constant there, okay? So this just only comes from 0.5 hertz, and in this 0.5 hertz over the entire sky and the spin down range that we've seen, we haven't seen anything. So what do? We imagine a population of sources that are distributed uniformly in the sky with uniformly distributed cosiotas, polarizations, and in frequencies in that 0.5 hertz with the noise of the detector in that 0.5 hertz. And we, for each of these sources, for each of these signals, we do a Monte Carlo and we measure what 2F we would have gotten, what detection statistic value we would have gotten. So we have a distribution of the 2F values for this population and at fixed H0. And we find the H0 such that, say, 90% of the 2F values of the population for that H0 are larger than the measured 2F star. Okay? And that is the 90% confidence gravitational wave upper limit. So, to recap, we set up a population of sources, and we measured the at fixed H0. We say, let's imagine that they all have the same amplitude. We let the other parameters vary, and we measure the distribution of the detection statistic values. And on each of these distributions, we measure what fraction of these sources had a value of 2F higher than the one that we've measured. Okay? When we find the H0 such that that distribution, okay, has 90% of the sources of the population higher or equal to the value that we measure, then we say that the H0 for which we found that distribution is our 90% upper limit, which means that what does it mean in practice? It means, well, we haven't measured anything higher than our 2F star. Then we can say with 90% confidence that our H0 must be smaller than that 90% upper limit that I've just described to you, how it's set. And it must be so because if it were higher, we would have measured something higher than what we've measured with 90% confidence, okay? And this is a frequentist upper limit because that confidence really is a measure of the basically fraction of the times that if that population was the true population, we'd expect a value of 2F higher than the one that we've measured. And this is actually quite simple. It's just that when one says it, it seems a little bit complicated, but if you take like 2 minutes to think about it on your own, you'll get it really quickly. It's just that saying it is a bit involved. Now, frequentist upper limits, this is an example of a frequentist upper limit, but a very clean and simple one, and also one where I'm going to show you results based on it, so I wanted to explain it well. There's other ways to set upper limits, for example, Bayesian upper limits. And in Bayesian upper limits, well, it's somewhat more natural, perhaps, because the result of a Bayesian analysis is actually a posterior probability on the signal parameters. So out of your machinery, in come the data, and in come the data, the signal parameters and priors on the astrophysical parameters, and out pops a posterior probability on the signal parameters given the data. And this is proportional to the prior times this thing, which is the likelihood, which is to zero order basically our sort of frequentist detection statistic. So it's the probability of the data given signal parameters. And so once you have this object here, okay, you choose the signal parameter that you want to get an upper limit for, and you derive the posterior for that simply by marginalizing the posterior that you've gotten. Here there's the prior missing, okay, with respect to all the other parameters. So in this case, if you want the posterior on H0, you marginalize with respect to post-iota, the polarization angle, and the initial phase, and then simply look at the posterior. Here is a posterior from the LIGO first science run search. So this is the posterior PDF, and these are the possible values of H0, which are really pathetic compared to today's standard, the 5 × 10 to the minus 21. This was a high-frequency pulsar. It was J1939 plus 2134 that emitted gravitational frequency around 1300 hertz. But a few times 10 to the minus 21 is order of magnitude higher than we can set now. But the reason why I'm showing you this is not so much these numbers, is the fact that here was the posterior probability. And you know, this says that basically this looks very much like a non-detection. This is what a detection posterior probability would look like. So this is consistent with 0. The bulk of the probability of contains 0. This is what things would look like for a detection. It means that if you took this as the most likely value, then the 90% credible interval for the signal amplitude would be probably in this range, okay? So this is something. This is the posterior with a signal. This is a posterior without a signal, and it's actually the one we got from analyzing the data in 2001, right? And so then, in this case, once you have the posterior, the upper limit is simply how far do you have to integrate in H0 until you get 90% of the probability. And this was the 90% upper limit value, which was 3 point something, okay? So this is if you have a posterior probability for your signal parameters, and this posterior probability is consistent with a non-detection. So typically, the bulk of the probability contains 0. Then you simply integrate out to whatever confidence you want, 90%, and that is your 90%, 95, 85% confidence upper limit. So this is the Bayesian approach. Okay, sorry. Okay, and these are the results from the latest, the 01 results from searches on continuous gravitational waves from known objects. And I know that Alicia has showed you this plot already, but since I talked about Bayesian upper limits, I wanted to tell you that these are in fact the blue stars on this plot are the Bayesian upper limits for the non-pulsars. And so each of these is actually a search with one template, because in the case of known objects, from the electromagnetic observations, we know everything about the objects. We know where they are, so alpha and delta. We know the frequency, and we know the frequency evolution. So we have everything we need to construct one template. We do that one templated search, and we get, in this case, actually a lot of different pipelines were used, but I'm going to concentrate on the one that produced most of these results. That's run by our colleagues in Glasgow. They are the ones specializing in searches for continuous waves from non-pulsars, and they've done this since S1. And it's amazing to see the increase in sensitivity, and these are the blue dots. And so these are actually upper limits, they're 95% upper its derived simply by integrating the posterior Bayesian probability. Do not worry about these pink things. The line here is the estimate of the sensitivity, which we always do before we do an analysis, and then cross-check that our analysis results sit where they should. In this case, they do. And the one thing I want to point out is some of these blue dots here have a pink halo around them. And these highlight the objects for which we've actually set an upper limit which is more constraining than the spin-down limit. Okay? So the spin-down limit is an important quantity. For objects for which we know everything, in particular we know the frequency and the spin-down, okay? We can ask the question, well, if all the rotational energy that the object is losing, and we know that it's losing because we know the spin down, so it's spinning down, it means the rotation frequency decreases. It means that it's losing rotational kinetic energy. If all that we were so lucky that went into gravitational waves, so it means that the ratio between the gravitational wave emitted and the spin down, that means the kinetic energy that is lost, was all due to gravitational waves, what amplitude would that correspond to? And you can compute that, and it's given by this formula. It's simple, with x equals 1, because that's the fraction of the gravitational wave energy to the spin-down energy. And then you can, when you have a result from your search, you can ask yourself, well, how does that compare with this quantity here? Because we would expect, obviously, that we cannot measure, the object will not be emitting at ANH0, which is higher than this, okay? So the really interesting results, in fact, are the one where our upper limits are more constraining than this, because this is something that we can derive without any gravitational wave observations, okay? And so these are the objects, the ones that have this pink halo, for which our upper limits are in fact the measured ones from the gravitational wave observations are more constraining than the spin-down limits, which are these triangles. So you see the triangles are typically below the star, the corresponding star. So these are our measurements. Each of these points has a triangle somewhere down here, and it says you've measured this value here from the gravitational wave observation, but we actually know already that H0 can't be bigger than this. But there are about a couple of handfuls of objects for which actually the spin down limits are higher. Okay, so those are actually really interesting. And so once we have our upper limits on H0, we can actually express them as upper limits on the ellipticity if we know the gravitational wave frequency and the distance. Okay, and so we can ask for all these objects for which we have upper limits at different frequency, what is their ellipticity? And I want you here to not worry about the lines, just worry about the blue dots. The blue dots are where the blue stars were in the previous plot. And so as a function of frequency, this is the ellipticity values, right? So the upper limits on the ellipticities. It means our results say that the ellipticities of these objects have to be larger than the value that you see here. And so you see that there's the population of, of objects which are above about 200 hertz, which, well, perhaps 300, 250, which are well below 10 to the minus 6. Okay, so these are very respectable ellipticity values. Now, the trouble is, though, that for all of these, we know that the spin-down ellipticity is, in fact, sometimes even 2 orders of magnitude lower. So, as much as these are respectable values, the fact that we haven't detected anything is not surprising because the spin-down ellipticities are quite lower. And conversely, it seems like there's no way to win here. The ones for which we did beat the spin-down limit, you see the pink halo, orange halo around our values, and there are some triangles above the blue dots. These are the ones for which our upper limits are more constraining. Yes, but the ellipticities here are incredibly high. They're 10 to the minus 4. These are very high values of the ellipticity. Okay? And this is the distribution of spin downs ratios. Yeah?
I had a question regarding what are those, do you have like first some intuition how we have so high spin down limits for certain of these that because everyone else seems to be pretty much below what currently light is doing, except for those few. Like, what is the physics of those pulsars that we, at least our theoretical limit was actually this much larger than the rest of the bunch? Or is it just like coincidence somehow, or is there something we?
Well, the reason why the spin down, here's the spin down limit sort of formula for, so the H0 is, the spin down H0 is this combination of F dot over F, and then epsilon, which is what we have, is proportional to H0. So it's when the parameters, there's, conjure up to have, for example, a very high F dot, then you can get a very high spin down value at lower frequency. You see, this is why they're here, typically at much lower frequency than these millisecond ones. So this is a bit sobering. The large majority of the objects that we know are not detectable unless there is some reason why the inferred spin down limit is in fact lower than the one associated with the gravitational wave emission. And the ones for which we do beat the spin down limit, their corresponding ellipticity values are so high that it's very unlikely that an object could sustain such high ellipticity. So are we done? And some of us think that no, we can look further because there might be a contact object that we do not observe that is close enough and bumpy enough that in fact it could be emitting gravitational radiation at a level that we can detect. And the rationale for this is that we only know of a few thousand pulsars, but in fact, in our galaxy, we expect there to be a lot more, orders of magnitude more. And estimates are that there might be up to 10 to the 7 EM quiet neutron stars within our galaxy. And so perhaps there is potential here in the band where LIGO is sensitive, which it is a smaller band and certainly does not seem to contain the bulk of the population that we see, okay? There is potential here for a object that to us right now would seem a not so typical one. Okay? And so this is why people do all-sky surveys. And all-sky surveys are surveys where you look blindly. Sometimes they're called blind surveys, but I don't like that name because this is the blind surveys. No, all-sky surveys. Blind in the sense that you don't know, you're not targeting a specific known objects, okay? And so we have to target different waveforms, many, and have to search explicitly now over many different frequencies, spin downs, and sky positions. And so not to scale, this is our unknown hidden pulsar somewhere outside in the galaxy. This is us with our 2 or 3 detectors on Earth going around the sun. And so these detectors obviously move because the Earth is spinning around its axis and moving around the sun. And so the signal that we receive from a pulsar, or the detector, will have frequency modulations, which are the orbital modulation, yearly modulation due to the Earth orbit around the sun, and then also the daily modulation due to the spin around its axis. So the way that a signal appears to us, a gravitational wave signal, it appears with a wave shape that is effectively different for every sky position in the sky. And it's different because this motion here, the motion of us with respect to different sky position, okay, is different, and this is encoded in the Doppler modulation. Okay, so each sky position, a Doppler modulation, so practically a different signal. And so this means that we have the possibility, if we look at the signal, to figure out where it's coming from. So this is the upside of it. And how many different waveforms we can distinguish is basically the same as for aperture synthesis for radio telescopes. This is the guy who got Nobel Prize in 1974 for figuring out that you can synthesize coherently the input from many different telescopes with a baseline of many kilometers to have the resolution of a dish with that kind of aperture. That's the concept of aperture synthesis, okay? And we basically do the same with our gravitational wave observations. The data that we get when the detector is here are combined with the data that we get when the detector is here, so many months after, okay? And we do this coherently, and we get basically the resolution of a baseline that is the radius of the Earth around the sun. And so with many months of observation, if we want to coherently combine the data, we're looking at a resolution which is arc seconds at 100 Hertz, and of course increases with increasing frequency, all right? So what do? We take the most sensitive method, we take our whole data set, 1 year of data, and we set up a template bank with the appropriate resolution, and we start marching through the template bank. And actually, soon we realized that we're not going to get anywhere, because even though it's great that the signal-to-noise ratio, the squared, grows with the time baseline of the coherent observation, this is because we're combining coherently the data. So even though the signal is very, very weak in a given moment, we basically sum it up coherently over the entire observation time. Our resolution becomes so good, arc-second resolution, that we would need to cover so many templates that we don't have all the computing power in the world to do it. Okay? So we have to resort to other approaches which alternate using the most sensitive methods that are these coherent observations. We can't do them fully coherently over 1 year, 2 years, many months of data. We have to chunk the data in smaller segments, analyze each of them coherently, and then somehow combine them. And I think Alicia has already sort of introduced the idea. Okay. Anyway, this is the idea. As I said, you divide your data set in chunks, which are doable computationally. They're not months of data, they're at most days of data. And on each of these, you do a coherent search. And then you have the detection statistic values for different templates, for different segments, so different times. What would a signal look like? Well, a signal would look like an enhanced detection statistic value in each of these segments, all right? And notice that the parameter space point, this gridding here, is supposed to show you the gridding in parameter space in any one or multiple dimensions, okay? And what I wanted to show you with this is that the place in parameter space where the maximum detection statistic occurs is not actually the same at every segment. Now you could ask, why is that? The signal parameters stay the same, so how come I don't get the same parameter point, the same waveform with the maximum at every segment? Well, the short story is that there is always a mismatch between the actual signal parameters and the template parameters. And this mismatch, the entity of this mismatch, changes in time. And so whereas at segment number 1, the closest template, the one that yields the maximum detection statistic value, might be template A, segment B, because the mismatch has changed, because, you know, this is a dynamic problem, the closest template might not be quite that one, might be one that is a little bit off, and so on. And so this is why you don't get the same template being rung off as the maximum detection statistic value for every segment. But how, you know, what template actually gets chosen at every segment? So the track in parameter space tells you something about the, allows you to refine the position of the actual signal with respect to this coarse grid. But this is a side point which you can forget about. And just what you have to understand is that you basically can track the signals, the possible signals, through the different segments. And so you do this by setting up template grids and combining the points differently. And combining means summing them, okay? So you sum F1, F2, F3 on this track and get an average value of the detection statistic. So in these semi-coherent methods, the detection statistic is an average detection statistic, okay? Because you're summing the detection statistic values along different tracks to get an average value of the detection statistic. And I want to say perhaps Alicia talked to you about the half transform, where you do this, it's basically the same concept. You do exactly this summing, but instead of summing the actual values of the detection statistic, you only sum zeros and one, depending on whether the peaks are above a certain threshold. And this can be very useful when you have very disturbed data, but it's the same concept. So in a semi-coherent method, you do coherent searches on the different segments, and then you combine the data by summing one detection statistic value per segment. How you choose it depends on the specific track. And you sum on very different tracks depending on sort of a fine grid in parameter space that you've set up. The overall SNR will scale like the square root of the coherent time baseline. So these are the segment length. And then, like, if you can neglect this W, like the fourth root of the number of segments. Now, we do two types of surveys of this type. The very broad, hopefully fast turnaround surveys with a short coherent time baseline. It means that these segments, the duration is small. It can be, you know, a few hours, okay? And you see the sensitivity scales with the coherent time baseline, the square root of the coherent time baseline. So they're fast, and the computational cost scales with a much higher power of the coherent time baseline. So these are fast because this TCO is a few hours, okay, even half an hour at very high frequencies. But on the other hand, they're not very sensitive. Then there are other surveys where this TCO is a few days. Now, these are very expensive. They're much more sensitive. And so they're the deepest array. But we have to balance somehow, and so typically they're limited in breadth. They don't look at 1500 hertz. Okay? And on the archive, you will find two papers that have been submitted in the past month, which actually look at O1 data and detail the results of all sky surveys on O1 data of the two different types. And I think Alicia must have talked to you about this. And so about these ones, the fast turnaround ones. And so I am going to concentrate on these instead, because these are actually the ones that I do. I was wondering if you need 5 minutes.
We probably have coffee now, actually.
Ah, okay, right. So you do need, actually you have more.
Come back at 1:45.
Okay, a 1:45. Oh, wonderful. You've got. So I hope I just recapping briefly, because I thought some of you were going to sleep at the end of before the coffee break. Bottom line is, most sensitive methods, coherent searches for observation times that span many months, not doable. Got to find a different approach that is computationally doable. So instead of taking one segment months long, we split the segments up, analyze each of them coherently, and then combine them incoherently. These are the so-called semi-coherent searches. You want the TCO, the length of the coherent segments, as long as possible to increase the sensitivity. Trouble is, when this increases, also the resolution increases, hence the computational cost increases. So in the end, there's two different compromises. One's where this TCO is quite short, so they're less computationally expensive, less sensitive, but can go broader in parameter space. And then the searches for which the TCO, the coherent length, is longer, that means days, they're deepest, they're much more computationally intensive. And so they usually have to compromise in breadth of parameter space. These are the two recent papers on the archive that detailed results from O1, okay? And you've probably heard about this, so I'm going to concentrate on this. And as you can see, we only spend 80 hertz. And the reason why we decided to concentrate on 80 hertz was that, in fact, this had been a frequency range, especially the one below 50 hertz, that had not been searched very much, especially with LIGO data before 01. Of course, having heard that we were going down to 20 hertz, they decided to go down to 20 hertz too. But this search was more sensitive. You can see, though, that the spin down range is smaller. So we go, down to -3 times 10 to the -9 hertz per second. They go down to -1 times 10 to the -8. So these are significantly larger spin down. All right, so I said I was going to concentrate on this search, and I'm going to touch base on three things. One, I'm taking the opportunity to tell you something about Einstein at Home, because this is our main computational infrastructure to do these searches that would otherwise be completely impossible. Then I'm going to show you how instrumental artifacts and dealing with them, so the fact that the data is not Gaussian, is what has driven a lot of the development and the in the new techniques, and even in sort of how we set up the pipeline. Okay, and then I'm going to show you some results. So to give you an idea of, after all this effort, in the end, what's the science that we can extract. So Einstein at Home, who's heard of it? Ah, nice. And you've all got it running on your laptops and your computers? So this is a volunteer computing project where, as you know, you donate the idle compute cycles of your machines, and you help us do the science, you help us analyze the data. In return, you get a screensaver. Really cool. Well, and well, if you do detect something, I think you get more than a screensaver. You actually get a certificate, and I'm sure there'll be a lot of buzz around the first continuous wave detection, so you get a lot of publicity. But the people, Science at Home is also used to look for EM signals from pulsars, X-ray and radio. And we have made detections on EM data with Einstein at Home. People have gotten certificates, have featured on the web page. Now, it's built on the same infrastructure as SETI at Home, but it was conceived for gravitational wave data analysis. And it was conceived way back in 2005, when most of you were probably just about babies. And it was publicized as part of the American Physical Society World Year of Physics activities. So this is how we were approached, and we started it. And it used the infrastructure and help from SETI at Home. SETI searched for extraterrestrial intelligence. And it's built upon BOINC, which is the Berkeley Open Software Infrastructure for Network Computing. And so it provides support for a variety of platforms, because, of course, it has, the more platforms we're able to run on, the more computing power we can leverage. So the idea is the following. You can't run a search on Einstein at Home unless it is trivially, you can divide it up trivially in small tasks, which are completely independent. And in the case of continuous wave searches, that really applies, because remember, we look for a nearly monochromatic signals. It means a signal whose frequency is basically constant. It means that all we need really to do the data analysis to look for a signal at a certain frequency is just a small, very small portion of the data around the frequency of the signal throughout the observing time. And so the data can be very nicely partitioned in small frequency bands that then get shipped together with the set of commands and the application used to analyze them. And so this is what, see, this is the data, gets divided in little frequency bands. These are the computational tasks, pieces of the sky, frequency and spin downs. And a combination of the data plus the application and the command line arguments is what we call the work unit that gets sent to the volunteer computer, that crunches on it, typically for a time that varies between 6 and 12, 18 hours. This depends obviously on how powerful the computer is. And then what we get back is a list of results. And this list of results does not contain results for all the points in parameter space that the computer searched, but only for the top few thousand, okay? Because otherwise there'd be too much traffic, network traffic. So we have to keep that down, and also we could never analyze all the results. So we're only interested in the top list, the most significant, so many. And so these are all coming back, and then we do the post-processing. So this is pictorially, conceptually how it works. Of course, there are some inefficiencies that are built in because we can't, we actually ship each work unit twice because we have to build in some safety against possible malevolent tampering with our results. And we put a result as valid in our set of results only when it validates independently from two different volunteer computers. Now, Einstein at Home is not a type of sleek machine. It's like a heavy lifting machine. It's not particularly elegant, but it gets the job done. And it's built to be robust, not to be pretty. But it does wonderfully. We have over 1.5 million hosts and 1 million participants who have done work for Einstein at Home over its life. In the past 2 weeks, I looked up, we have had about 50,000 hosts active, corresponding to about 30,000 participants. This delivers to us, not just to the gravitational wave search, but also to the EM searches, overall about 5 petaflops of sustained computing power. That's an enormous amount of computing power. It's a few times what together the dedicated LIGO and Virgo clusters can provide, several times that. And Einstein at Home would be in the top 500 list. And here I thought it would be interesting perhaps to see how the hosts are distributed in terms of a CPU brand and operating systems. And so our applications need to be very robust, and because they need to run on a variety of operating systems and architectures. And we're in fact now thinking also about porting some of these on GPUs in order to leverage that computing power too. This is the screensaver that you get. And what happens is that it will show, here you see it here, what point in the sky the application that you're running on your computer is pointing at the time. And so where your computer is idle, you can see that how you are actually contributing and what data is being analyzed. So please sign up here and contribute. All right, so this is our computing infrastructure. What do we use it for? Well, to do these semi-coherent searches. And I talked to you about the F statistic, right? This is the typical coherence statistic. Alicia has derived it for you. I've seen her slides, so I know that. Although, from your faces... Anyways, there is a reference in this talk to the original paper. It's a very nice, elegant and relatively simple derivation. If I had to do it here, I would spend 1.5 hours doing that, and I don't think that's particularly enlightening. But if you're interested, go and take a look at it. So it's the coherent detection statistic that we use, and that is basically a maximum likelihood method that tests the signal hypothesis against the Gaussian noise hypothesis, okay? So you ask yourself, does this data contain, is it more consistent with a signal plus noise or just with noise, okay? And the noise is Gaussian noise. And so since our data is not perfect, in fact it can contain all sorts of sort of burst glitches, which people who are familiar with searches for binary and spirals or burst searches know plague the distributions of events, right? But it can also have coherent disturbances, so very weak, like monochromatic signals of terrestrial origin. And even if those are not on all the time, even if they don't have the perfect Doppler modulation that an astrophysical signal would have, they do match, even if only for part of the time, the signal model a lot more than Gaussian noise, which means that the detection statistic values that we get can be highly increased just because of the presence of one of these disturbances. So it's not just the signal that can trigger the high detection statistic values, it's also noise disturbances that look more like the signal than Gaussian noise. For example, a line in one detector. So we've developed a statistic that has a more sophisticated hypothesis. It doesn't just ask the question, does it look more like signal plus noise or Gaussian noise? We develop a composite noise hypothesis. We ask, does it look more like a signal, or does it look like a Gaussian noise or a line? Okay, so we've gone from an F statistic, which is basically test the signal against Gaussian noise hypothesis, to a more sophisticated statistic that tests the signal hypothesis against a composite noise hypothesis, Gaussian noise or a line. And the line is defined as a signal in only one detector. This was the starting point. Now, this is really the idea. The rest is algebra. And we don't have much time. So I think I'd rather give you the idea, and if you're interested, you can look at the algebra. The algebra is very powerful because it allows you to turn this idea into actually a detection statistic, so something that you can compute in order to test the hypothesis. And the result is not trivial. And again, I'm putting it here, not because I expect you to understand this right now, but because I want you to understand the ingredients that go into it. And the fact that the algebra, coming from this very simple idea, will actually allow you to define a quantity, okay, that you can compute on your data that now will have a better performance. It's going to be a detection statistic that has a better performance in the sense that I will explain with respect to certain types of disturbances. So instead of the statistic itself, we use a monophonic function of it, the log. This is because when you do the algebra, you find out that if you work with the logs of the odds ratio in this case, they're mathematically simpler expressions. But you will know that any detection statistic is equivalent to any monotonic function of it. So it's okay, since the log is a monotonic function. And the ingredients that go into these are, okay, there's a prior on the signal versus line hypothesis, so you must have some kind of prior on the lineness content of your data. This is the average F statistic, the thing that you would compute without knowing anything about line robust statistic. Here is a scale factor that you actually have to introduce and you have to tune the machinery for. And this is basically tells you, okay, at what scale of detection statistic amplitude do you think that what you're getting is so high that it can't be Gaussian noise anymore and it's got to be some kind of disturbance? So you have to know your data and try and insert that. These are the single detector. X here indicates the detector. This is the single detector prior online at that certain frequency range that this detection statistic is computed for. What is your prior on lines. Is this a disturbed region of the detector spectrum? Okay, and this is the single detector detection statistic, okay, which you can compute. And this F double dot max is again just a function of the transition scale and the single detector detection statistic, the Gaussian noise hypothesis one, plus the correction factor that has the priors on the line content from the single detectors. So, of course, you can't understand why this right now, and this is what the algebra tells you. This comes out of the algebra if you do it starting from a very simple idea, which is this, okay? Which you test the signal hypothesis against a composite line hypothesis. There's really not much more than this. The rest is algebra. And you get, though, an analytic expression. So let's see if it works. So here, please concentrate only on the lines I'll point out. On the left, there is, as a function of frequency, the noise content. So this is basically the power spectrum of the two detectors, LIGO detectors, L1, Livingston in red and Hanford in blue. This was a 6 date, I believe. And this, you see, is a fairly, I'm going to ask you, does it look to you disturbed or fairly quiet stretch of the spectrum of the detectors? Disturbed? Okay, this was actually fairly quiet in the sense this is if you look, it's these are exponentially distributed as they should be. This is disturbed in the sense that there is a line. Okay, it's in the frequency domain. You're usually used to seeing these plots in the time domain, but for continuous waves, it's the frequency domain that tells you usually more. So this is actually a pretty good stretch. There's no big outliers. The statistical properties are uniform. And here we have the detection probability for a set of injections done as a function of the amplitude of the injected signal. So it's normalized with the power spectral density, which is constant. Okay? And concentrate on the comparison between the red curve, this one, the one with the stars, which is the standard F statistic, and the new line robust statistic, which is the blue. Okay? So you can see that this whole, that as we expect, if we haven't screwed up our new line robust statistic, in the case where we don't need the line robust statistic because there's no disturbance in the data, the performance is comparable. Okay? First check. You need to make sure that in the case where the data is not disturbed, your new statistic doesn't degrade your detection probability. And you can see that it doesn't here. Okay? But let's take a look at the case where in one of the detectors, okay, we actually have a disturbance. This is a line. It means that in your detectors, in one of them, you have a sinusoidal-like signal. Okay? In the other, there's nothing. The blue one is pretty much like this data. And when you look now for a signal, the performance of the F statistic, you see, is impacted. See, here at lower signal strength, you lose detection probability with respect to your detection abilities if you use the new detection statistic, which is robust. Because the new robust statistic recognizes that, hey, okay, I got a value of the detection statistic which is higher, yes. But now let me test if this is higher because it's really a signal or because it's a coherent line. Okay? So here is where this hypothesis comes in. Now the noise has the hypothesis in that there might be a line in one of the detectors. Okay? And so it recognizes it here, and it can discriminate between the signal and the noise better. And so this is an example where you can clearly see that the line robust statistic, the new robust statistic, does its job and does not lose detection efficiency, whereas the normal F statistic would. These are illustrations of the same concept. And instead, what I'm going to jump to and point out is that this is important. It is important because if you remember well, when I was talking about Einstein at home, I pointed out that each result that is returned to us by the volunteer computer is a top list. So what happens is you search for different waveforms, and you will search for something like 10 to the 9 from each work unit. You can't return to us 10 to the 9 results. You just return the top 10,000, 5,000. So the top. Now it's important that the top are not junk. Okay? So the importance of setting up statistics that can distinguish between the junk and the signal better is that your top list become more valuable. Okay? You get in the top list the points which might really be more likely to host the signal rather than the points that have elevated value just because you have a coherent line in one detector. Okay? And I want to show you how impressive, in fact, this looks. Typically, as we gather all our results, different work units will come in and they will look at different parts of the sky for the same frequency and spin down range. And the first thing that we do is we gather together all the results in 50 millihertz bands, and then we look at them. And so this is a result where we have, as a function of f and f dot, all the points in the sky in this frequency, 50 millihertz frequency band for the entire spanned range of f dot values. And you can see that here, this is what we would call a disturbed band. There is clearly not uniform statistical properties. The color code and the height here is the detection statistic, and it's 2f, average 2f. What happens when we use a robust line statistic? Well, it looks better. It's not as disturbed, which means that a lot of the points that seem the most disturbed did not make it into the top list, and some others that are more likely to actually host the real signals have made it. And this is a robust statistic like the one I described. It tests against this composite line hypothesis. We actually went further because we realized that a lot of our disturbances that still, you can see, this didn't kill everything, so to speak. There's still something in here. So there's still some noise that's not Gaussian, that's not just a persistent line in one detector, that's produced at elevated values. So we realized that what those were transient lines. So we can get values, elevated detection statistic, if we get a line which is there in just one detector, which is very loud, even only for a short period of time. Short means, say, a few hours, a couple of days, compared to the 10 days of the coherent stretches. So we expanded the noise hypothesis to also include the transient line hypothesis. So now we developed a detection statistic, was robust against Gaussian noise, lines in one detectors, and transient lines. And we call this the BS for signal, G, Gaussian, L, line, and TL, transient line. Ta-da! It worked. And again, this is very important because it means now that if we use this detection statistic to rank the top list, it will not be, we won't get parameter space points, okay, from the elevated values of those detection statistics that weren't able to distinguish that there was something that was noise. Okay, but even these are not perfect. So even with these very sophisticated, robust detection statistics, we still find in our results, even in the BSGLTL ranked results, sort of bands that look disturbed. These, fortunately, are a very small fraction, a few percent. And so upfront, typically, from the analysis, we exclude them, okay? Because it's hard to deal with bands whose statistical properties are so different than the sort of undisturbed ones. And then we look at those separately. So after having excluded stuff that looks like this, which is only a few percent at this point, we look if there is something outstanding. And what does outstanding mean? Well, outstanding means something like this. And this you might recognize because... Sorry? Yes, it's the first detection plot. This was the plot where you could see from the CBC search the significance of GW 150914. And this is the detection point, so the value of the detection statistic that was measured, and this is its background. I would say this is its background. Which of the two, it's actually something I can't explain right now. But what you basically want is something which sticks very far above the noise background, okay? And this certainly did. So when we look at our results, first of all, we need to ask, is there something that sticks clearly out of the background? And so what we do is we take our results in 50 millihertz bands, okay, and we look at the loudest in each 50 millihertz band. And here, for the S6 all sky analysis from last year, you can see the values of these loudest over 50 millihertz band plotted as a function of frequency. And here you can see that the loudest value, the loudest means the highest value of the detection statistic over 50 millihertz band increases with frequency. And can anybody guess why? Here's a hint.
Number of points?
Increases, yes. That's exactly right. This is the number of points in the sky that we search at 50, 60 hertz. And this is the number of points in the sky we search at 110, 20 hertz. It's that the number of points scales with the square of the frequency, okay? So here it is. So you've done more trials, and so, as we were saying, I was saying at the beginning, the maximum that you measure increases. And this in red is the expectation value with the 1 sigma bar. So, okay, good. Is this significant? Is there anything significant? And so what we plot here is we turn each of these loudest measured values in a p-value. And we look at the distribution of p-values, which is what's plotted here in blue, and we compare it with the expected, with the 1 sigma. And from this, we conclude that we have something very interesting. Good. No, we don't. We don't, absolutely not. Okay, and just to make sure, what is a p-value? Well, it is the false alarm probability associated with whatever detection statistic value. So it's the probability to have measured something as significant or more than what we've measured. And this can be computed analytically if you have the distribution of the actual variable, and you know how many number of independent trials you actually have performed. Okay, so this is the probability density of the detection statistic times n, because you've done n different trials, so there's n possibilities for it to have a value in this range, times n minus 1 probabilities for the remaining n minus 1 values, right, to be lower than that. So this is the PDF associated with a maximum which is measured at a certain value. And so this is how you derive the p-values here that I've shown in this plot. So you can derive, in fact, the PDF, which means you can derive the expected value, the points, and the sigma. And then you can compare them with actually what you've measured. Okay, so what happened with the O1 data? This is the search I was telling you about. We used 12 segments, each 210 hours long, so a few days, nearly 10 days. As I said before, we looked at only 80 Hertz, and this took a few Einstein at home months, about 4 months on Einstein at home. And in spite of having used a robust statistic and having removed the clearly disturbed bands, as I showed you before, like we did in a 6 data, we still got many outliers. These are, in half Hertz frequency bands, the loudest 2F values, okay? And the 1 sigma expectations are dark pink, the 2 sigmas are lighter pink, so you can see there are many, many points that exceed the 3 sigma. And so if I compute for a 1, the search I'm showing you the results of, the expectations, okay, versus the measured, you can see now that we definitely cannot claim the same sort of agreement that we saw in a 6. We have tons of outliers, which is bad news because since we don't expect to suddenly see a whole population of pulsars, this is probably due to the fact that the data has a lot of coherent disturbances that even our fancy detection statistic didn't catch. So what do? We can't just say, we haven't seen anything, we place an upper limit. We can't say that. So what we do is, well, we have to set a threshold and actually follow up all this stuff. But we don't want to follow up just the complete junk, the really loud things. So we take a band where the distribution is fairly well behaved. We wish all the bands had this distribution. Here is the detection statistic, here's the count, okay? And we put a threshold at about here, 5.5. This is a threshold such that if the data was Gaussian without all these disturbances, we would probably get a few candidates per 50 millihertz band that then integrated over 80 hertz would yield about 2,000, over 2,000 candidates in all. Instead, if we put a threshold here, we find 15 million candidates. Okay? So this gives you an idea of how disturbed the data is. With this threshold, if all the data looked like this, we'd expect a few thousand. We got 15 million. And now we got to follow up each of them and figure out which is a signal and which isn't. So this is, though, remember, we put a threshold here. So we are getting, this is a sort of a sub-threshold search. Even if the data was completely Gaussian, we'll still get a few thousand candidates which are not which would not be significant enough at this stage to be claimed as detections, because noise alone would produce candidates that significant. I said about 2,000. Okay? So this is a version, a mild version of a sub-threshold search. It's something we do by necessity because we have so many disturbances. So we use a scheme which is a sort of a follow-up scheme, which basically tries to zoom in each of the candidates. And on each candidate, basically we search at higher and higher at every step resolution and smaller parameter space, and see if at every step it actually exceeds the threshold that becomes higher and higher for a candidate signal. Okay? So at each stage, we reject more and more noise, and the accuracy on the signal parameters increases. And each stage is a semi-coherent search, apart from the last. So here are the 3 stages that were used. Stage 0 is the original search. You can see what happens. Basically, at every stage, the coherent baseline increases, basically doubles. until the point where stage 3, where this becomes a completely coherent search using the entire observation time. And this is the thing that if we did it on the entire parameter space would not have been possible. Okay? But the number of candidates that survives from one stage to the next decreases. And this is why we can do more and more sensitive searches and more computationally intensive ones. Okay? So this is the number of segments, and you can see that the resolution decreases. This gamma here is just a factor that you have to divide the resolution in spin down by in order to get the final sort of fine grid resolution for that stage. So here would be 1.3 times 10 to the minus 13. And this is the resolution in the sky for this equation. So the first thing we have to do when we have 15 million candidates, if we got to reduce them even before we start doing any follow-up. And the idea is this. Both signals and noise can yield high detection statistic values over large parameter space portions, which are correlated. And so it's actually, there's no need to follow up each point separately. You recognize that these points are correlated. These all come from a noise disturbance, okay? And you don't follow each one of them up separately. This is noise containing a disturbance, and this is instead fake signal plus noise. Even a signal can produce something which is quite, let's see, extended in parameter space, okay? And you don't need to follow each of these up separately. You can actually sort of cluster them together, okay? Call them candidate number 1. It's got to be somewhere in this area with these parameter values. That's the idea of clustering, okay? This is a signal which is weaker, and so it extends a lot less, but still there's a number of candidates here, okay? So this, okay, was comparison and undisturbed band.
Excuse me?
Yeah?
Does Einstein and Home do that already? Or
No, we do it before. We do before. On the results that come back. So because these are the Einstein and Home results in 50 millihertz bands. We look at them, we recognize that there's elevated detection statistic values close by in parameter space, and we cluster them. And the clustering is actually a tricky business, because the question is, how do you identify these excess and overdensities? And you know, what is exactly the clustering? Suppose you have a criteria to associate them. What you do is you start from, let's say, the loudest here. Let's say you pick the loudest. And what you do is you look for nearby candidates which you associate with it. Okay? Once you've identified them, let's say all this chunk here, you remove them from the list of candidates. You tag them with a nominal value of the parameters and a certain uncertainty. You remove them from the list, and then you move on to the next highest, which will be this. And you say, is there an overdensity around it? If so, you do the same thing over and over again until you have no more candidates. And a lot of these clusters are going to be single occupant clusters, because here, for example, after you remove this bunch, you don't really see, perhaps this might have these two friends here, but a lot will be just single occupants, okay? And setting up this procedure is actually, you know, not trivial, because you have to do it in a way that adapts to the data. So measures the overdensity depending on the data. And we've done this, and you can see it's a new adaptive procedure that sort of adapts itself to the actual distribution of the data. So if there is a large disturbance in parameter space due to noise, it will cluster everything together. It doesn't work just based on what we expect from a signal, because that might be a lot smaller. So here is how it worked in the top plot for data containing, in fact, a fake signal. This is the clustering that's first done in the frequency NF dot, and you see the blue points are the ones that are clustered together. Then it takes these same plot points here that have been clustered in F and F dots, so recognized as close enough to each other around this primary maximum, and says, well, which of these are actually also clustered in the sky, okay, around the maximum. And so the subset of these that are also clustered in the sky, that's what constitutes a cluster. And so in the end, the blue points here. This is a case instead where no cluster was found. Starting from the highest here, this was just noise. There was no clustering, no sufficiently nearby overdensity, neither in frequency and spin-down space, nor obviously in alpha and delta. So this was a single occupant cluster, okay, to give you an idea. And the distances are defined based on, this is the distance in frequency F dot, is just the frequency of every candidate around the frequency of the maximum, normalized by the frequency or frequency derivative spacing. And here you can see the distributions for these quantities for one of these clusters. And based then on the shape of this distribution of distances, close to the first minimum, the cluster radius is set. This again is to give you an idea of the type of intricacies actually of the techniques when you have to even implement a relatively simple idea. So there's parameters that need to be tuned that depend on the type of search that you're doing. If it's a low threshold search, it's a high threshold search, because obviously how much the signal that you're looking for you allow to stick above the noise is a very important quantity when you're dealing with overdensities of noise candidates around it, and on the specific search setup. So it requires some Monte Carloing, Monte Carloing, to understand how to set these. In the end, for the O1 search, to give you an idea, in the sub-threshold search, which is the one that we looked at, the noise rejection was as high as 90.5%. It means if we had 15 million candidates in, we rejected about 91% of them. So we ended up with less, not really we rejected them, we clustered. And so we ended up with about 10% of these as cluster centers, and with a detection efficiency which is about 96%. Okay? And this was comparison with an older procedure, which wasn't adaptive. So this allowed us to go from 15 million candidates to 36,000. Okay, much better. So now we've only got to follow up 36,000 candidates. Each of them has its own uncertainty region around it. And so we do the first follow-up. This is the input. They're actually 35,693. This is how they're distributed with respect to BSGLTL. And this is the uncertainty volume that we searched around each candidate. Okay? And we searched it, and this is the distribution that we found for the candidates after the first follow-up, which had a coherent time baseline, which was double, nearly more than double the 210 hours. And we set a threshold at 6 in the detection statistics, so here, because we know that if a signal at the previous stage exceeded the previous threshold, after this search, it would have, with very high confidence, exceeded this threshold. Okay? And so anything that's below can be thrown out. And so when we do this, we're now left with 14,456 candidates that survive. And the uncertainty around them has decreased. Okay? So now we have 14,500 candidates, and each of them is even a smaller uncertainty. So now we can increase the time baseline of the coherent search even more. We double it, more than double it. We go to 1,260 hours. We set a threshold based on very low false dismissals for signals that would have passed the other stages, again at 6. And now we find that 8,500 survive only. And the uncertainty associated with these is even smaller. Okay? And so for each of these 8,500 candidates, we search this even smaller parameter space region around them with a time baseline, which is again twice for each segment the previous one. And this is actually now the full coherent, the full observation time, okay? We again put a threshold at 6, significance in BSGLTL, and we find that 6,349 survive. And this is the uncertainty associated to it. Okay, so we are left with over 6,000 candidates. We have done a fully coherent search. Now what? It's a bit of a problem, right? What do we do now? Well, we started thinking. And, you know, these candidates are not Gaussian noise fluctuations. There's no way Gaussian noise can survive all these stages. These must be, again, some sort of coherent disturbance that passes through a line robust statistic, which are great, but you know, there's a lot of tuning and they still let a lot of things through, especially things like this, which are quite subtle. You've seen that there's in the sort of visual inspection of the results, you couldn't see big statistical anomalies. These are relatively small disturbances. So we thought, well, long-lasting coherent disturbance is less likely to exhibit the astrophysical Doppler signature that a signal has, right? I mean, what's really special about our signals is that their frequency has to change in a very precise way. It's the one that's dictated by the motion of the Earth around the sun, around its axis, with respect to that very specific source. We can still get elevated values of the detection statistic for wandering lines that change a bit, and the spin down that helps. But, I mean, if we turn off that Doppler signature completely, and we see the value of the detection statistic increase, this should be a smoking gun for something that's definitely a disturbance rather than a signal. So we decided to do a search with a different template bank. It's a template bank where the Doppler modulation is completely turned off, but we left in the amplitude modulation so that you still have some, we're not looking for just sinusoidal signals in the data. There are still some amplitude variations that can take place. This allows our sort of non-physical template bank to adapt better to possible disturbances. And also we end up with the same statistic as in the real search, so still a chi-square with 4 degrees of freedom, which makes the comparison a lot simpler. So first of all, we wanted to get an idea of how safe this was. So how different is this bank of template waveforms from our astrophysical ones? And so the way to quantify this simply was to produce some fake astrophysical signals, okay, and then do a search with the usual template bank, so a template bank that is actually matched to that astrophysical signal, and our non-astrophysical template bank, the one with the Doppler modulation off. And so since we removed completely any noise because we just wanted to investigate the properties of these different families of waveforms, what we get from the search is basically the SNR squared, rho squared, of the D mod on waveforms and D mod off waveforms. And if these waveforms are very different, what will happen is that this will be high because this is the SNR of a signal that's been searched with exactly the right template for that signal. And this is the SNR of an astrophysical signal searched with our non-astrophysical signals. So what we hope is that this is much smaller than this, and so this is very close to 1. This will tell us that these two waveform families are quite different, and so our veto is probably going to be quite safe, because there's no chance that we might accidentally veto out a real signal. And so what you find here is the mismatch, so this quantity here, which we would like to be close to 1, as a function, okay, here's of the ecliptic latitude, and I'll comment on this later, but for now just concentrate on the y-axis for 3 different families of signals at 3 different frequencies. The highest is the gray and the lowest is the blue. So first off, you can see that this mismatch never goes below 93%. So I think this is pretty good. And it goes to lower values of the mismatch, indicating, you know, more consistency, slightly more similarity between the non-astrophysical waveform family and the astrophysical waveform family for the lower frequencies ones. And that's actually quite intuitive to understand. Why? Because what we've done is we've switched off the Doppler modulation. Doppler modulation is proportional to the frequency, right? And so the Doppler signature is higher for higher frequency waveforms. So for the lower frequency ones, actually, the Doppler signature is not that strong. So if you turn it off, you're still going to get something pretty different, but not quite as different as for the waveforms with the higher frequency. I mean, it's still quite negligible. I mean, we go from 99% to 93%, but things behave as one would intuitively imagine. And for the same reason also, you see perhaps a slight drop as you approach the poles. The poles is the place where the sky, in the sky, right, where you have the smallest relative velocity, which means the smallest Doppler signature. And so it's the place exactly where the unphysical and physical waveform families would look more similar with respect to the equator. Okay, so all this makes sense, and it's very encouraging. And so now we go on and construct this veto. We basically want to compare the modulation, the results from the original search with the results from this Doppler modulation off search. And how do we do this comparison? Well, just based on what these 2F values are, which are the log likelihood, the ratio of the 2 likelihoods would be the difference of the value of the 2Fs. Okay? So we use the difference of the values of the 2F, and we have to set thresholds. And in order to set thresholds, we do an injection study. So we inject signals, and we measure the 2F from the original search and the 2F from the DMOD off search. And we set the thresholds here in such a way that no astrophysical signal would be rejected. Okay, so this is a safe way. We don't know what this will do to the noise, and it's very hard to tell because we don't have a way to model the disturbances, but what we can do is make sure that we don't accidentally veto out a signal. And so this is how we decide the signal threshold that has this form. As a side remark, this actual DMOD off search is not so completely computationally negligible, so it actually has to be done in 3 steps. But for now, this is a technical detail. And this is, I wanted to show you graphically what happened for one candidate picked at random. Okay? This was the candidate from the original search, right? The mod on. And this is the, this candidate hence was below 400. It was at 120 or so. And this is what happened when we ran the D-mod off search. You see how much the value of the detection statistic increased? Okay, so quite a smoking gun that shows that this object, the candidate, the cause of this candidate, is clearly more likely to be of terrestrial origin than of astrophysical origin. And it also tells us more if we look at separately the results of the D-mod off search for the two detectors. We can see that the culprit here is the Hanford detector. This is the one that must have had the coherent non-astrophysical disturbance. Okay? Just graphically. So then we run our actually multi-step D-mod off veto search with the thresholds that I just explained here. These were 6,000 candidates, and you see that all but 4 lie in the rejection region. So this was, I think, a very happy moment when we actually applied the veto to the data, and we saw that out of 6,350, we got rid of all but 4. The 4 surviving candidates, again, what do we do? These are the parameters. Well, by that point, we had O2 data. The run wasn't finished, but we followed it up. We followed them up using O2 data. That's the only other thing you could do at this point. And we used directly a completely coherent integration, completely coherent search over 2,000 hours. We said, well, if this 2F is due to a signal, we could project what the expected 2F would be. And this is what's plotted, what's shown here. This would have been the 2F expected if these had been real signals. These instead are the 2F that we recovered that are actually consistent with the expectations for noise. And so we conclude that it is unlikely that any of these 4 candidates actually stems for continuous gravitational wave signal, which is a very sad conclusion, but it is what it is. And this was to give you an idea of actually what it means to battle the detector artifacts and the coherent disturbances when you look for a signal that has certain features that are quite aligned with this type of disturbances. We don't have, right, time. What I'm looking.
How much time do you need?
I think 5 minutes. Yeah. So I just wanted to show you, now that we say we don't have a detection, then we're back to our usual upper limit business. So what can we say on the gravitational amplitudes of the objects that might be there? If they're there, they've got to be lower than this curve here. And this is the curve that came from the search I just showed you. And this is the O1 search. These are the previously existing upper limits from S6 data. So this is why we decided to look at this frequency range, because as I said before, it hadn't been explored very much. In fact, below 50 hertz, we only had Virgo data results. So we improved very, very significantly on these. These are the results from the broad parameter space search that Alicia has talked to you about. You see we're about a factor of 2 more constraining than those. And we're looking at upper limit values, which at 90 hertz are about 2 × 10⁻25. Now, what ellipticity values do these correspond to? Well, you have to ask, obviously, you have to insert a parameter, which is the distance of the source. Unlike in the non-pulsar case, we don't know what distance the source might be. So if the source were at 1 parsec, okay, then we could say that we've excluded objects with ellipticities greater than 10⁻⁷ within 1 parsec at frequency greater than 60 hertz. Now, 1 parsec, what's the chances that there is an object within such a small radius? Quite small. So obviously, there's larger and larger chance that you might actually have 1 such objects as you go out further. And within 100 parsecs, which is sort of the order of magnitude, I mean, we do see pulsars at a few hundred parsecs. So at 100 parsecs, this was able to constrain the ellipticities to values lower than 10 to the minus 5, okay, for frequencies smaller than 60 hertz. Of course, the ellipticity are less constrained at lower frequencies. This is just the noise of the detector. Okay. From the broader search, the one that's about a factor of 2 or more less sensitive, we see at higher frequencies, the ellipticity values become smaller, and particularly, above 200 hertz, again, within 100 parsec, we can now constrain ellipticity to be less than 10 to the minus 6. Okay, so remember that these pulsars for which we beat the spin down limit, the ellipticity values are up here, 10 to the minus 3, 10 to the minus 4. Here in blind searches, we are constraining the values in ranges of ellipticities that are, quite dignified, lower than 10 to the minus 5, and in a lot of the spectrum, even 10 to the minus 6, within 100 parsecs or so. But still, we haven't seen anything. So I'm always asking Niels, at which point does this become interesting? Okay, so I'm finished. I just wanted to recap the basic concept of signal detection that we've looked at: false alarm probability, p-values, trials factor, how this impacts the sensitivity in large parameter space searches, means when you look for many, many different templates. What are upper limits, frequentist upper limits, Bayesian upper limits, and what does it mean then, the spin down upper limit. And from there we went to talking about broad blind surveys, Einstein at home. I illustrated these recent results. I talked about the robust detection statistic with composite noise hypothesis, how that anyway sometimes fails and you need to set up multi-stage hierarchical approaches, how that sometimes still leave you with thousands of candidates, new leaders that you need to think about, and then the astrophysical reach. So I hope this will help you to read and understand better some of our observational papers. Some of you are authors on many of these papers. I know you're busy, but I suggest you do take the time to read each one that comes out. And of course, I know that Einstein at home. Thanks.
Any questions? About them 4 candidates, if there are some objects observed by video or optical,
There aren't.
have you?
Yeah, we looked.
Why?
Yes, yes.
If there are something, you change conclusion about there's no story there, or
Yeah, so there's a lot of assumptions in our searches, okay? And especially after a procedure like the multi-stage procedure that I described. And the basic assumption is that the phase coherence of the signal is maintained across, the O1 observation time, and then is maintained consistently to O2. So this is our, let's say, vanilla standard CW signal. And that is not there. Now, could there be a less vanilla flavor signal? Of course, something that did not maintain phase coherence completely. Something, for example, an object had a glitch. It could have glitched multiple times. It could have glitched significantly during O2. To some extent, some of these factors we have taken into account. So the exact answer to what could we have missed and what this actually null detection result applies to depends very much on how you could imagine this non-vanilla signal to be. And so if we want to talk about that, you know, we have to look at the specific model, and then I can tell you to what extent and what loss in detection statistic we could have occurred. So the statement here really applies blanket, like I made, to a strictly phase coherent gravitational wave signal that would maintain such phase coherence to a large extent for long observation times, even covering the period between 01 and 02.
You mentioned that you dealt with just single detector lines. Did you think about looking at sort of transient coherent lines that pop up for a couple of days and then go away again?
Well, this line veto deals with these because these are going to be, if a disturbance is going to be due to a non-astrophysical signal, no matter for how long, no matter in how many detectors, if it doesn't have the astrophysical signature, then the detection statistic that you get from this non-astrophysical class of waveforms that doesn't have the Doppler modulation on, but still allows for some varying, both in wandering terms because it has the spin down and spin up component, as well as varying amplitude. This will catch it, and you'll get a more significant detection statistic value with respect to the astrophysical class. And these, in fact, are exactly the type of things that the line robust statistics that only focused on a single detector type of artifacts, just because analytically they're easier to fold in, did not catch. So for the coincident artifacts, the robust Bayesian statistics do not catch them. This does, in short.
When you do the comparison between the two waveform families, the Doppler modulation on and off, that like a faithfulness test, did you look at the effectualness between these two families?
Did I look at what, sorry?
The effectualness between the two families.
What do you mean?
So allowing parameters of one of the family to change.
Oh yes, oh yes, because these are, it's folded in because the searches here for which we derive these are searches over a parameter space out of which we pick the maximum. So it's folded in.